Today I'm going to talk to you about the experimentation and simulation of a shell and tube heat exchanger. To give a background information, it is important to know that heat exchangers provide thermal energy transfer between two or more fluids at different temperatures. In addition, computational fluid dynamics it is a useful tool in the analysis of this type of equipment. In order to characterize the heat exchanger, the next equation was used to find the heat transfer between the fluid in the tube and the one in the shell. To calculate the heat transfer coefficient, the resistances and dimensions of the exchanger were necessary. Additionally, parameters of the heat exchanger and the differences between the two configurations have to be taken into account. These differences are shown in Figure 2. The assembly methodology in Figures 3 and 4 respectively was managed for the experimentation. 3 flow rates for the cold fluid and 3 temperatures for the hot fluid inlet were used during the data collection. For calculations, 3 methods were applied: LMTD, Kern, and Bell Delaware. For LMTD, the heat transfer was evaluated using equation 4, where the variables change according to the configuration as seen below. It is important to note that some adimensional numbers were used, like the Reynolds and Prandtl numbers, as well as the Darcy's friction factor, as shown in equation 12. With the friction factor, it is possible to calculate the pressure drop. Finally, the convective coefficient is needed and can be evaluated with the Nusselt number. Now, for the Kern and Bell Delaware methods, the overall heat transfer coefficient for both of these is found using equations 17 and 19 respectively. These methods allows to calculate the convective coefficient and the pressure drop with the following equations. It's important to note that assumptions made for these methods are that for Kern it is assumed that the pressure drop is proportional to a number of cross-flow sections, while in Bell Delaware assumed that the fluid in study has a turbulent behavior with a really high Reynolds number. Now, for CFD modeling, mesh models and parameters shown in this slide were used. Prism layer measure and embedded thin measure are especially important, as prism layer measure allows the simulation to capture accurately the fluid's behavior near walls, and embedded thin measure is useful for capturing solid thickness of the tubes, as it creates prismatic layers in the volume of the solid, allowing a better modeling of the heat transfer. For the physics models, important models in the liquid includes the kappa epsilon turbulence model, approved for having low computational time while giving accurate results, the polynomial density, which must not be assumed to be constant for the liquid, and the two-layer all-wall plus wall treatment, which permits well modeling in different Y plus ranges. For the solid, constant density was assumed, and segregated solid energy model was applied to model heat transfer through the tube's thickness. Now we can see in Figure 5 mesh seen in the exchanger's geometry. In the results section, it's able to observe that the global heat transfer coefficient was calculated using 4 different ways, including the CFD simulation. Some differences can be shown, and this can be explained by the assumptions each method has. Differences in the results were considerable, especially for pressure drop. For the CFD modeling results, we can first observe in this animation a vector scene of the velocity. It can be noticed how the velocity in tubes is much greater than the ones in the shell, and that some vortices and swirls are formed in the shell. Also, it can be seen how the baffles change the shell's fluid trajectory and the magnitude of velocity, which can prove that there is not a single flow regime in the shell. Now, we can observe the pressure profile in the shell and the tubes. Here the pressure loss can be appreciated. Results from the ones calculated are great, because in this case no extrusion in the inlet regions of the exchanger were made, which makes the fluid to get into the exchanger with a not well developed regime. Temperature profile for countercurrent and parallel configuration is shown here. It is noticeable that in this case of parallel configuration there is a lower temperature difference between the hot and cold fluids in the inlet and outlet zones, different to the countercurrent configuration, where temperature differences are considerable along the exchanger, making this configuration more efficient. Also, it can be noticed how baffles allow the fluid inside the shell to mix, making different temperature regions in this part. In this slide, we can see the magnitude profile in both configurations. Something important to highlight here is that baffles make the velocity in the shell to decrease along the exchanger, and lower velocity regions correspond to regions of better heat transfer. In this slide, we can see that the heat transfer coefficients are lower for the shell fluid than for the one in the tubes. Also, it can be seen how regions where temperature differences are greater, heat transfer coefficient is greater. These regions are where there is contact between the tube's fluid and the solid, and between the shell and the solid. Here we can see the Y pulse values. In the shell they are slower because the velocity was lesser and because of the prism layer in the mesh. However, in the tubes the velocity is greater and no prism layers were in the mesh, in this case, which explains the great range of Y plus values. Now, in discussion, we can see so very important parts at the differences in Bell-Delaware's method and Kern method, and for the simulation, the discrepancies. In conclusion, it was observed that there exist more differences between the heat transfer coefficient, pressure drop, and other parameters in the calculations due to assumptions in models and mistakes in the simulation as the missing structures and prism layers into the tubes. Besides this, baffles are important in heat exchangers design, as they increase the heat transfer area and allowing a mix of the fluid and regions of lower velocity which permit better heat transfer. Finally, velocity profiles show that the flow regime in the shell is not constant and requires an appropriate modeling. Also, from the temperature profiles, we can conclude that countercurrent configuration results more efficient in heat exchangers performance.